Okay, so we have another rotational kinematics problem. We have a wheel on the left, and it's attached. There's a rope attached around it, and there's a weight, a block, at the bottom of the attachment. The block is 1.5 kilograms, and someone's like holding it, so the system is at rest, meaning nothing is moving. And then the block will get released. The 1.5 kilogram block will get released. It will then cause the wheel. The block will go down, which will cause the wheel to spin, right, in this direction, clockwise. Okay, and so once it starts spinning, what we're going to do is we're going to let it spin for 2 seconds, and then we're going to figure out what the kinetic energy is of the wheel after 2 seconds of spinning. Okay. So, and then this wheel, like the shaft that it's on, right here, the shaft that it's on, there's no friction. So it's frictionless, okay? So let's think about this from an energy perspective. Nothing is moving, right? So initially, nothing is moving. So there's no kinetic energy in the system. But is there potential energy in the system? So does the wheel have potential energy? No, it doesn't, because the wheel doesn't go up or down. But the block does, right? The block does have potential energy. So initially, the block does have potential energy. So we'll say the potential energy of B, meaning the block. It's going to have some amount of potential energy, right? Stored up. Think of it like a battery. And then once it goes down, once it's here, let's say, and then once it descends to here, let's say it's up here, and it's gonna go down, right? Well, when it does that, it's gonna lose that potential energy, so that energy is going away. Okay, so then what's going to happen to the energy? Well, that energy is going to be transferred. That potential energy that it lost. Remember the law of conservation of energy. If you lose energy somewhere, then something else had to pick it up, right? So if it lost potential energy because it went down, it went closer to the Earth, so to speak. Where'd that energy go? Well, it got turned into kinetic energy. Oh, the kinetic energy of the block? Well, no, both. So the block is still moving. Nothing at the end of 2 seconds. The block is still moving, but the wheel is also moving. So the potential energy really got converted into the kinetic energy of the block plus the kinetic energy of the wheel. Right, so you have to balance your energy out. So the energy is not, remember, it's not created or destroyed. You just kind of move it around. So the block is like a battery, and it had some amount of energy, and that energy got distributed or changed into kinetic energy of the block and the wheel. And if there were friction around, where the wheel was spinning in the center, then obviously some energy will be lost due to friction, due to heat, right? But in this scenario here, there's no friction, so all the energy is accounted for. Okay, great. So I need to find out what the potential energy is of the block. Actually, before I talk about that, so this wheel is spinning, right? Well, initially it's not spinning, and the block is underneath it, and then once the block is let go, it starts spinning. But all mass resists change in motion. So that's what Newton's second law is about. Force is equal to mass times acceleration. And what this means is it mass, if you were to, like, say, push a mass or whatever, put a force on a mass, that mass does not want to change, so it's going to resist. And so the bigger the m, the bigger the mass, right here, then let's say you were looking for your acceleration. So you would divide by m, so it'd be F divided by m equals a, right? And so acceleration is inversely proportional to mass, meaning if mass gets bigger, acceleration goes down, right? If mass gets bigger, then your acceleration goes down. And so you can think of F equals ma is a law about inertia, meaning the more mass you have, the more inertia, meaning the more resistance it's gonna apply. Okay. Same thing for this wheel. So Newton's second law. Let me just erase this. So Newton's second law, F equals ma, right? But that's for linear motion. But there's an analog for rotational motion, and instead of force, you have, it's called tau, which is torque, right? Which is force in a rotating object. Equals, and instead of mass, you have the moment of inertia, which, remember, is just mass and how mass is just distributed along the radius. And then A, of course, is linear acceleration, but in rotational, it's alpha. Okay, so we have tau equals IA, and so that's the radial form of F equals ma. F equals ma is for linear motion, and then tau equals I alpha is basically Newton's second law, but in a rotational context. So mass, where it's linear, if you try to push it, the mass is gonna resist that change, right? It's the same thing for rotation. If you try to rotate a wheel, it's gonna resist that change, and so that resistance ends up manifesting itself as this tension. So right here, you can see there's 9 newtons of tension in this rope. That tension is because why? Why is there tension there? Why isn't there zero tension? It's because the rotating wheel is resisting going down. It says, no, I don't want to go down. I don't want to go down. And so it's resisting. And what is it doing? It's trying to pull up, right? So the mass of the wheel is trying to pull up. Even though there's no resistance in the center of the wheel, there's no friction. The mass itself is resisting. So that 9 newtons represents how much that mass is resisting change, because it doesn't want to spin. Well, once it starts spinning, then it's fine. But it doesn't want to change. So if it's at 0 meters per second, meaning when the wheel's not moving at all, it's gonna resist. Anytime it tries to change whatever its velocity is, if its velocity is 0, if its velocity is 1 or 2 or 3 or 4 or 5, whatever its velocity is, if you try to change its velocity, it's going to resist it. Okay, and so that 9 newtons just means I'm going to resist that change. Okay, so I'm just basically the site aside is just showing you that Newton's second law is really about, well, yeah, sure, it's about forces and acceleration, but it's also about inertia. Things that are at some velocity, if you will, do not want to change their velocity, right? The bigger the mass, the more it doesn't want to change. Okay, it's resisting it. All right, so remember up here we have, if we go back to this PE, so our energy formula, we have the potential energy of the block. Well, what is that? Well, what is potential energy? The formula for it. Well, it's mass. Oh, I'll go back. That's not what I want. It's mgh. The mass of the block, 1.5, times gravity, which we know that, which is 9.8 meters per second squared, and then h. H is how far it dropped. Remember, it's a battery. It's like a gravity battery. Once it descends down, we're gonna get rid of that. We're gonna use up that energy. Okay. But so the question is, I know m, I know g, but I don't know h. How far did it drop? Okay. So what we're gonna do here is we're going to do this. We're going to do a diagram like this, and we're going to look at all the forces on it. This is now we're looking at just the block, okay? So the forces pulling down on the block are mass and gravity, right? That's the force going down, and then on pulling up is T is the tension. Now the tension, it already gave it to us, which was 9 newtons, right? And then on the bottom, it's mass, which is 1.5 times gravity, which is 9.8. All you gotta do is multiply those two together, and you get 14.7. 14.7 newtons. Okay. All right, great. So now that we know all the forces in the y, of course there actually are no forces in the x. Then we can use Newton's second law to find out what? How fast it's accelerating down. Because if it was in free fall, it would just fall at 9.8 meters per second squared, right? But it's not in free fall because the wheel is resisting the change. So what we can do is we can say, what are the sum of the forces in y is equal to mass times the acceleration in y. Right, we're just going to look at that component, just the y component. So what does that look like? Well, 14.7 is actually going down, so that's technically negative 14.7 because that force is pulling downwards, and then we have a plus 9 newtons, which is pulling up. So we have a plus 9 going up, and then a negative 14.7 going down. So that's the force. That's the sum of the forces in y. That's that equals the mass, which we have is 1.5, and then the acceleration. Well, we don't know what it is. We're trying to figure that out. So if we do 14.7 plus 9, and then we divide by 1.5, get rid of that, then we have our acceleration is 3.8, negative 3.8 meters per second squared. All right, so that's how fast we're not going 9.8 meters per second squared. We're going 3.8 because the wheel is resisting our motion. Okay, so let's highlight that. That's our acceleration. That's probably important. Okay, great. So now that we know that, I like to make diagrams. So if we did this like this is velocity. Okay, and this is remember we're starting out. Then this is in meters per second, right? We're starting out at 0, remember, because it starts at rest, because the block isn't moving. And then it's going to travel down, right? And so this, at a constant acceleration, and this constant acceleration is 3.8. So the velocity, as a function of time, is negative 3.8. Because negative 3.8 is actually the slope of this line. 3.8 t, because this is time, plus 0. 0 is the y-intercept. We don't have a y-intercept because it started at rest, but I'm just showing you, okay? Okay, so we have its velocity is 0, and it's going to go, and we have its slope. This is 0 seconds, and then this is 2 seconds. So what we know is this thing is going to go for 2 seconds, right? So if I have 2 seconds, then I know the velocity at time at 2, which is seconds, is equal to negative 3.8 times 2, of course, which is 7.6. So this here, that's a little bit off, is negative 7.6 meters per second. So that's how fast it's going. At 2 seconds, it's going negative 7.6 meters per second. And so then the question is, well, how far did it travel, right? So now I know it went for 2 seconds, and at 2 seconds, it's now traveling. It started at 0, right? Started at 0, and then go faster, and at 2 seconds, it's now going 7.6 meters per second, down. The negative means it's going down. But how far did it travel in that period? Well, if you remember, if you have a velocity versus time graph, the area under the curve represents displacement, because basically it's velocity times time, right? So velocity, remember, is meters per second, and then time is in seconds. And if you multiply those together, you're going to end up with just meters. So that's going to be if you're looking at the area under the curve for velocity versus time, it's just displacement. So I have a triangle, right? Let me make this a green color, right? I have this green color, and I'm trying to find the area of this triangle. Well, what is it? Well, of course, area equals 1/2 times base times height. 1/2 is 1/2, base is 2 seconds, and the height is negative 7.6 or 7.6, okay? Well, it's negative. So the area is technically negative because it's underneath the line. See the 0 line, the horizontal underneath it. So technically the area is negative, like mathematically speaking. Okay, so 1/2 times 2. Well, basically the half and the 2 cancel each other out, and so we're left with 7.6 meters. So it is 7.6 meters, but mathematically speaking, we're just put a little negative there, just letting us know that it's underneath the line. But yeah, what this means is it displays 7.6 down, because remember the block is like here, and it's going down like here. So you could think of it, and if this is 0, think of this line as 0. If it went up, it would be positive 7.6 meters, and because it went down, it was negative 7.6 meters. Okay. All right. Well, we now know that. So we now know how far we went down. Okay, so 7.6. So if we go back to our thing up here at the top, MGH, this right here. So we know our mass, M, 1.5. We know the G, which is 9.8. And now we know how far it went down. At 2 seconds, it went down 7.6 meters. Right? So if you do all that together, 1.5 times 9.8 times 7.6 equals 111 joules. So that's how much energy was lost from the battery, like the gravity battery, right? That's how much it lost. But then it was picked up, it got converted into kinetic energy of the block and the wheel, right? So what's the kinetic energy of the block? Well, you may remember kinetic energy of this of linear motion of the block is 1/2 mv squared, right? And so yeah, so if I want to know kinetic energy of the wheel, it's the formula, of course, is kinetic energy equals 1/2 m, remember, is I, and then v, of course you need I is moment of inertia, and then v is in an angular sense, it's omega squared. So if I wanted to find out what the kinetic energy of the wheel, I would have to know its angular velocity and its moment of inertia. I don't really have any of that stuff, but I do know the kinetic energy of the block. It's 1/2 times mass, which is 1.5, times v squared, and the velocity at the time at 2 seconds. Remember, because the kinetic energy is changing as every second. As the block gets faster and faster and faster, its kinetic energy is always changing, right? Well, its potential energy is changing too. But at 2 seconds, remember, right here, it's going 7.6 meters per second. So if I use this, if I do 1/2 times the mass, which is 1.5 times 7.6 squared, right, and do all that, you end up with 43 joules. So that's 43 joules for that's the kinetic energy of the block. And then, of course, all you have to do is, the only thing you have left is just this, kinetic energy of the wheel. And all you have to do is take the 111, subtract the 43, and then you end up with the kinetic energy. Because 43 plus something has to equal 111, right? And so that ends up being 68 joules, okay? So I didn't actually need to know like the radius of the wheel. I didn't need to know how the mass is distributed or anything like that. All I had to know is like how much battery did we use? 111 joules, okay. And then how much of that energy was used up by the block? Well, 43 was used up by the block. So that means the remainder had to be used by the kinetic energy of the wheel. So just process of elimination. So yeah, so that's it. So what is the kinetic energy of the wheel at 2 seconds? It's 68 joules. So anyway, so yes, this little lesson was really about still angular motion, but about kinetic energy and how or energy, how we change potential plus kinetic, and how these energies can change. And also remember, it's also about inertia. F equals ma, which is about inertia in the linear sense, and then tau equals I alpha, which is about inertia in the rotational sense. And just if you forget anything, remember that mass resists changes in velocity, so it resists those changes. Okay. All right, that's it.